minimum, I don't have a, who has a, is this it? No, that's a pen. Right, a penultimate, that means next to last. The next to last minimum, where eventually you jump to the side of a potential, slide down a hill. In this minimum over here, we have eternal inflation, bubble nucleation, slide down a soft, slow ramp. That's called slow roll inflation, and eventually wind up with ordinary cosmology in here. All of standard model cosmology began someplace along this slow ramp here, and the rest of it is, as I said, standard model cosmology. All post-standard model cosmology is everything that happened before, including this very, very complicated landscape. The question is how to test it. And by test it, I mean more or less direct test observational tests, how to test this idea. And that's what I'm going to talk about, the phenomenology of it. I have not a lot to say about it. Unfortunately, one is very, very limited. The problem is exactly the same as the problem in particle physics testing post-standard model. The better the standard model works, the harder it is to test the post-standard model. Maybe we should call this the pre-standard model, come to think of it. This happened before, not after. But there's a prejudice that I want to dispel before I start. The prejudice dates back to exactly when, I don't know, but it's the idea that if there is inflation, there must have been a huge number of e-foldings. There must have been a huge expansion factor, perhaps as big as 10 to the 1,000. I've heard the number 10 to the million, and I've even heard the number 10 to the 10 to the million as the expansion factor of the universe during the ordinary inflationary period. I strongly believe that this is very unjustified and is quite possibly wrong. It basically came from mixing up the two kinds of potential, there are two kinds of inflation, the eternal inflation and the slow roll inflation, which I think we have every reason to think are two separate phenomena, or maybe two, very likely two separate phenomena. We have to distinguish them, and when we distinguish them, possibilities for phenomenologically studying post or pre-standard model inflation begin to arise. Now, we'll have to be lucky, but let me discuss them anyway. The question is how much ordinary inflation did take place? Did it obliterate all evidence of an earlier epoch? Can we look back to when the universe may have nucleated from another point on the landscape? And if so, what will we see? And finally, I don't know if I have time to talk about it. I will, even if I do, it will be very brief. Can we see into other bubbles? Can we see into other types of environments? Of course, we can try to see them by looking into the past. We can also try to see them by looking to the side, so to speak. Okay, quick cosmology lesson. There are three kinds of cosmologies. You all know them. I won't go into them in any detail. The only thing I want you to know is that I will use, where is it? I will use the notation R, capital R, for a radial coordinate. And the rest of it you don't need to know, other than to say that there are three kinds of standard, absolutely standard cosmologies: closed FRW, flat FRW, and negative curved FRW. Negative curved has always been a bit of an orphan. Nobody's ever been quite as serious about it as the other two cosmologies. And of course, inflation tends to flatten everything, and so there's a prejudice in the favor of very, very flat cosmology. The best fit, the data is inconclusive on this, and it will never be, well, it may become conclusive, but in any case, the best fit is that the curvature is ever so slightly negative, but definitely zero is well within the error bars, slightly shifted to the negative. That one shouldn't take that seriously, obviously, but it may be that in the relatively near future, we will pin down the error bars on that much better. The anomalous behavior of low L primordial fluctuations may be another hint. Of course, it may just be an artifact and of no special interest. And I'll come to that. I'll come to what that means. But the question is, what does theory say? In particular, what does theory say about which of the three cosmologies is the right cosmology? And the theory, as I said, that needs to be tested is the theory of tunneling on a landscape. And the theory of tunneling on a landscape has a very, very definite thing to say. This is a picture, a sort of artist, I'm not much of an artist, but a picture of an eternally inflating universe giving rise and giving birth to other bubbles. The bubbles give rise to bubbles. I'm going to assume you all roughly know this picture. It has both a series and a parallel aspect to it. A given observer passes through a series of different vacuums. On the other hand, at the same time, there are parallel things going on corresponding to distant bubbles nucleated. And we can call the various vacuums ancestor vacuums, the ones which preceded our own, a remote ancestor, an ancestor, and here we are up here someplace. So that's the picture that, as I said, needs to be tested. Now, what goes on in the final vacuum, our vacuum, so to speak? Well, our vacuum, according to this picture, is a negative curved FRW universe. This goes back to the work of Coleman and DeLucia, who studied these kinds of bubble nucleations. And it's kind of odd when you think about it. An infinite negative curved universe embedded in what could be a perfectly finite de Sitter space. But of course, this de Sitter space, this is a Penrose diagram or a conformal diagram. The de Sitter space has a divergent metric up near the end of time. And so when you look at the spatial slices in here, they actually diverge at the corners here. And the preferred, as I said, geometry that would, not just preferred, required geometry that would occur from bubble nucleation would be negative curved FRW. So that's first of all, a first lesson. Now, here are the equations for a negatively curved, or for that matter, this is actually for negative curvature. This is the negative curvature term over here. This is the basic FRW equations. Everybody's familiar with them. This phi might be the inflaton. Here's the kinetic energy of the inflaton, never particularly important in anything I'll have to say. Here's the curvature term, negative curvature. That's the plus sign here. And of course, here's the potential, the inflaton potential, which may look something like that. It's not important whether this is, for the moment, a single field, multiple field, or whatever, just a tunneling from one point to a neighboring point. Here's where the eternal inflation took place, the ancestor vacuum over here. You tunnel out onto the side of this potential and slide down by slow roll inflation. During the initial phase of this, before you actually enter slow roll inflation, when you first tunnel out onto the side of the potential here, you're dominated completely by the curvature term. 1 over a squared is much bigger than anything else. And that leads to the solution of the FRW equations, which is the scale factor growing like time. That means an enormous amount of cosmic friction. This is the cosmic friction term in the equation of motion of phi. A dot is 1. A goes to 0 near the beginning here. And so there's an enormous amount of cosmic friction here. That's rather useful in slowing down the inflaton and making sure that it doesn't slide off very, very quickly to infinity. I call this the overshoot problem, but I'm not exactly sure this is what everybody else calls the overshoot problem. I have a feeling the overshoot problem, as it was originally defined, had to do with rolling over the edge here. But this is another overshoot problem here that you could conceivably get into trouble where you just overshoot the inflationary region altogether. And that you're well protected against by this cosmic friction term blowing up and being very, very large in the beginning. All right, so that's a good thing. Here's the history of the universe, same history of the universe. Within the FRW patch, it starts out curvature dominated. Curvature dominated means that it's dominated by the term which is much bigger than the vacuum energy in here, or than the inflaton potential. And then eventually, the curvature term shrinks down until it becomes no bigger than the vacuum energy. When I say vacuum energy, I mean inflaton potential energy along here. And you enter into the slow roll region. Eventually, you come to reheating at this point over here, and becomes radiation dominated. Eventually, the surface of last scattering, and here we are up in here somewheres. The problem, of course, is that too much slow roll inflation would obliterate everything that came before. Obliterate in the sense of observable signal. And so the question then becomes, how much slow roll inflation actually took place? To answer that, I think, or of course we can't answer that. I can't answer that, but I can make some suggestions about it. First question is, why did slow roll inflation happen in the first place? If you take a look at that potential, it's a rather odd potential. It's bizarre from the point of view of ordinary renormalizable quantum field theory. So it's not a natural, generic thing to happen, to have enough E-foldings of slow roll inflation to either to obliterate the signals that came before or to account for phenomenology. And as near as I can make out, the only answer around at present, the best answer around at present is, hold your ears, anthropic. Okay, so let me just very quickly go through the anthropic argument. Negative curvature means, from the Newtonian point of view, that everything was shot out at above the escape velocity. That raises the danger that when stuff is shot out above the escape velocity, that it is moving out too fast to turn around and create structure, in the universe. The problem is closely related to and similar to the problem that Weinberg addressed in, 1987, about the repulsive force of a cosmological constant preventing structure. Here it's not a repulsive force, it's just kinetic energy. Kinetic energy, outgoing kinetic energy can prevent structure formation. No structure, no stars, no Earth, no life, no us. So now given, this is a given now, I'm not going to try to explain this, that the primordial density fluctuations are of order 10 to the minus 5, we have to worry about how much curvature we can tolerate at the time of structure formation, negative curvature, and still get what we want, which is us. Right. Now, the answer is you can't tolerate a lot of curvature. So the question is, how did the curvature get down to the acceptable anthropic level? It got down to the anthropic acceptable level by a period of slow roll inflation. Slow roll inflation will stretch out the curvature. And so there's an anthropic bound then, a lower bound, on the amount of slow roll inflation that's necessary for structure formation. Here's some equations. I don't expect you to remember them. They're in a paper by myself and Freivogel, Kleban, and Maria Rodriguez-Martinez. But I'll tell you what the equations are very, very quickly. This is the inequality which, if it's satisfied, says structure forms. On the right-hand side is something involving delta rho over rho. At decoupling, and also at the time that you evaluate the rho over here is an arbitrary time after decoupling that you evaluate the inequality. It can be evaluated at any time. Both sides scale the same way. This is delta rho over rho at decoupling. What's over here is omega lambda, the vacuum energy due to the present-day cosmological constant, or divided by omega matter to the 1/3 power. And here is omega curvature divided by omega matter. Now, if you evaluate this today, then this term is negligible. If you evaluate it today, this is the big term here, and this becomes Weinberg's bound on the cosmological constant, the repulsive force of a cosmological constant, that if it was exceeded, we wouldn't have structure. On the other hand, we can evaluate it also at decoupling. At decoupling, this term is very small. This is the dominant term. And decoupling is, roughly speaking, fairly close to the time of structure formation. So this is the term to worry about. And what it says in practice is that the curvature has to be smaller than a certain amount. Here's the certain amount, which can then be translated into the amount of slow roll inflation that was necessary to bring the curvature down to this level. Expressed in terms of e-foldings. The nice way to express it is in terms of e-foldings. It is often said that observation, not anthropics, but observation requires greater than 50 e-foldings. Now, there's a convention there. Some people say 60, some people say 40. There's a convention there. It's the difference between the number of e-foldings which is important, but I'll adopt the convention that observation says greater than 50 e-foldings. In that convention, the number of e-foldings necessary for structure formation, people, life, is greater than 47.5. That I find interesting, that the anthropic bound is so close to the observational bound, and there's some reason to get a little bit excited. Now, to answer the question, of course, of how much e-folding took place, you have to have a theory of probabilities of, since we don't know for sure, and we can only make probabilistic arguments at the present time, you have to have a notion of measure on the landscape. How many regions of the landscape have this number of e-foldings, that number of e-foldings, and so forth. And the subject of measures on the landscape is in a primitive state, although I happen to think some progress is being made on it, not by me. But basically, there are two kinds of measures, as far as I can tell. One kind violently favors large numbers of e-foldings, just to make as big a volume as you can. But also, typically, those measures have very, very bizarre consequences of other kinds. There are just pressures, anthropic pressures and other pressures, which push you into some of the weirdest regions that you can imagine. And so I think this is something one ought to avoid. Other kinds of measures, and all of this measure stuff is phenomenological, at least at the moment. The other kinds of measures tend to be rather neutral with respect to the number of e-foldings. And the examples that I know are ones by Busso, Harnack, Cribbs, and Perez, and more recently an extremely interesting one by Guth and Vilenkin, which tend to be rather neutral with respect to the number of e-foldings. If it's neutral with respect to the number of e-foldings, then really what determines the statistics on the landscape is simply the number of vacuums of each type, counting the number of vacuums. And of course, I don't know enough about the landscape to really be able to answer that question, but let me make an extremely simple model, a very, very simple model of landscape statistics, that the inflaton potential in the slow roll region is parameterized by 3 parameters. The first parameter is a width. In other words, how long this ramp is. The second parameter is the height, v, and the third parameter is a slope parameter, x. X can vary basically from 0 to 1. I'm assuming that it's tilted downward. It can vary from 0 to 1. 0 is completely flat. 1 is a ramp which just tilts down to this point over here. Delta phi, this is a delta, not a lambda. Can that be seen? Delta phi, I had a very strong prejudice that it shouldn't be bigger than Planck length. I think from Eva's talk yesterday, there's a fairly convincing case to be made that it could be somewhat bigger than Planck length, Planck mass. But it really doesn't matter very much for my argument, because in both cases, this distance is bounded by something of order the Planck mass. Could be 10 times the Planck mass. But I will simply take it to be some bounded region. So the statistics should take place, or the statistics should involve delta phi's, which are of order Planck length, Planck mass, or smaller. And V presumably should have a vacuum energy. I can't see. +5. OK, let's go really fast then. All right. You do some statistics on this landscape, which simply means you assume equal probability on the distribution of the 3 parameters within the box defined by 0 to 1 or whatever. And you simply fix the number of e-foldings and integrate out the other variables straightforwardly. And what you'll find for this particular simple model is that it is hard to make a lot of e-foldings. The probability to make n e-foldings falls like 1 over n to the 4th. I think that's very characteristic. It's hard to make a lot of e-foldings. And I think with almost any kind of measure, you will tend to make a small number of e-foldings with a diminishing probability for a large number of e-foldings. In particular, for this particular example, the probability for greater than 50 e-foldings is 10 to the minus 6. So in that sense, inflation is rather fine-tuned. If we ask a different question, let us impose the anthropic constraint. Let us say we're here. Right? So, and the landscape is very big, lots of possibilities. Let's put the condition that n is greater than 47.5. If we do so, then we can calculate the conditional probability that n is greater than 47.5. What is the probability that n is greater than 50? And the answer is more like 0.9. So inflation seems to be highly probable given that structure forms, given that we are here. To my mind, this is at present the only known explanation for the fine-tuning of inflation. Notice that n greater than 100 would only have a probability of 0.1. Next question, what is the window? Oh, I'm never going to make it through this talk. What is the window that structure, pre-inflationary structure can be seen? The window that pre-inflationary structure can be seen is something like between 50 and 53. That turns out in this model again to have a probability of about 15%. 15% is small, okay? And I certainly recognize that. 15% is small, but not infinitely unlikely. Perhaps we will be lucky and be in this window. If we are, then all sorts of options open up for detection. There are various fossils. I'm not going to have time to explain them in detail. The first of which is negative curvature. Negative curvature at what scale? Well, negative curvature at a scale less than or equal to 10 to the minus 5 would not be interesting because just the background microwave, the ordinary CMB fluctuations are of order 10 to the minus 5. So we will certainly see curvature at 10 to the minus 5, equal probability that it's positive or negative. But curvature at the level of 10 to the minus 3, it's now at the level of 10 to the minus 2, the bound. Curvature at the level of 10 to the minus 3 would be very significant. In particular, if it was discovered to be positive at the level of 10 to the minus 3, this theory would get scrapped. So it is certainly falsifiable. There's no question of that. First prediction is curvature. No prediction about the magnitude of it, but the prediction would be that if you see it, it must be negative. I'm going to jump to the last slide here. Well, not the last one, but these are all beautiful and interesting. You don't know what you're missing. And I will be glad to explain to anybody who's interested. The second fossil that I just want to mention is very low L tensor modes. Now, why are there very low L tensor modes? Not scale invariant tensor modes, but tensor modes which are piled up at very, very low L. Again, the magnitude of them I can't predict, but the reason is they are inherited from the ancestor vacuum. The ancestor vacuum has a large cosmological constant, presumably, at least by comparison with the vacuum energy during inflation. And so, because it has a much larger Hubble constant, there will be a tendency to generate gravitational waves in the ancestor vacuum by the same mechanism that would generate them in the ordinary vacuum, except the ordinary vacuum has an energy a couple of decades smaller. So it could be, and should be, that in the ancestor vacuum, large magnitude gravitational waves, when I say large magnitude, I mean relative to what you might expect in this vacuum, large magnitude gravitational waves will be generated. The question is, to what extent do they penetrate into our region, and can we see them? The answer is calculated by Freiberg, Sakino, myself, and yeah, is, I'm going to give you a formula. I'll just write you down a formula. Where is it? Yeah, here it is. L squared, it tends to increase, it's very blue tilted with respect to L, but then there's a suppression factor, R to the L, where R is simply the radius that we can see out to in units of the radius of curvature. In units of the radius of curvature, the radius that we can see out to on the surface of last scattering. If there are exactly 50 e-foldings, we could see out to about an r equals 1. But we will not be able to see out that far. We will probably, at best, be able to see out to an r of a half, or something like that, according to the best guesses that I can make. And that means that this formula here will have a quick increase and a quick decrease. It'll be piled up somewhere around L of 2, 3, and 4. And the prediction would then be, well, I'm not even going to bother with this. The prediction would then be on large scales, the largest scales in the sky, seeing tensor modes, and those tensor modes, even if there are no tensor modes driven by ordinary inflation, and that would be my expectation if the vacuum energy is not bigger than Planck scale during inflation, then my expectation would be that you cannot see any tensor modes driven by ordinary inflation, but you still have the possibility of seeing these tensor modes, but only at the lowest L. In that case, without those tensor modes, the polarization in the sky would be purely E mode on large scales with those fluctuations you might see on the largest scale in the sky. Again, L equals 2, 3, 4. You might be able to see B mode polarization. So that's another signal. Do I have 1 more minute? Yeah, okay. The last fossil remnant, so we have negative curvature, large scale B mode polarization, and the last has to do with bubble collisions. This, I think, is less likely than the others. Just imagine here's today's universe. Here's a line that I have drawn. It is a time-like line. It doesn't correspond to anything, anybody in the theory. It's just a time-like line that intersects this point. There's an infinite amount of proper time along this line, and therefore it is overwhelmingly likely that another bubble will nucleate somewhere along it. All right. This was pointed out many years ago by Guth and Weinberg. Lots of people have studied it and commented about it. Vilenkin, Garriga, Freiberg, Boso, Schenker, Sakino, lots of people. Kleban, Yerkane, lots of people have been interested in possible signals of bubble collisions. Now, the only thing I'm going to say about it, two things I'm going to say about it. Again, this is something which would be wiped out by too much inflation. The signal would be wiped out by too much inflation. Again, you're best off with a minimal number of e-foldings, not much more than 50, 52, 53. One other point. Yeah, if it can happen once, it can happen again. And if it can happen again, it can happen again and again. And so the expectation would be that the outer boundaries of our space would be filled with bubble collisions. The only question is, can we see them? And a particularly interesting setup has been studied by Kleban and Chang and Levy. And I will tell you what they find. They find that if, again, very, very lucky, or for very lucky, a bubble collision might look in the sky like a ring with a region of I can't remember if it's cooler or warmer. Anybody know? I think it's cooler. A cooler region on the inside, that would be the visual evidence of the bubble. The bubble having deposited its gravitational effect in the CMB would cool it. But again, if there was too much slow roll inflation, like all the other fossils, it'll get obliterated. So we have to hope for a miracle. Good. Thank you.
So what about non-Gaussianity from the fact that potential is steep before you start inflating?
Yeah, that's an interesting question. If the potential were steep before, it depends on how steep. Depends on how steep. There's a critical curvature of it before you enter the slow roll region, where you go from a region in which the scalar modes are suppressed. That's if it's very steep and sharp, to a region where the scalar modes are enhanced, if it's too shallow. So you could get either. You could get the scalar modes enhanced or suppressed at low L. Now, we know it's suppressed at low L, so that could be indicative of something, but it could also be indicative of nothing.
I had another really silly question, but you showed omega k, the current bounds on it, and omega k was slightly negative. But isn't that positive curvature because a dot over a squared is equal to
Omega, I think I was showing curvature. It's, what did I show?
Anyway,
it is tilted towards the negative curvature side, slightly, but ever so slightly, and I took that off the.
so it is tilted to positive omega k.
What's that?
That's what you're saying. Okay.
What's that? I probably got it backward, but it is tilted towards negative curvature, but by so little that it's clearly not meaningful.
Historically, inflation was introduced to solve the fine-tuning problem of the old Big Bang model.
Yeah.
Do you feel that inflation has caused us to make much progress?
Inflation has done what?
Has inflation helped the fine-tuning
Well,
problem?
I think it substituted one fine-tuning for another. It substituted the fine-tuning of, well, you know what the old fine-tuning was. It substituted the fine-tuning of that for the fine-tuning of a certain potential. That's why I say that the only known explanation at this time of why there was inflation, slow roll inflation, was anthropic.
No, but isn't the label anthropic principle another way of saying fine-tuning?
Yes.
So I have a more technical question, I guess. So how sensitive?
I can't think of any question more difficult than that.
So it's you're assuming some prior distributions for your parameterization of potential.
Wait,
right?
say it again.
You're assuming some prior distribution, probability distribution for your potential parameterization.
Prior,
so how
yes.
sensitive is your calculated probability density distribution on what you assume about it?
Not a
For
lot.
example,
Not a
if you
lot.
take-
Not a lot. For example, I did an example with a curved potential, you know, with a parabolic potential, a few different parameterizations, all with 3 parameters, just because that's about as big an integral as I can do. And so all of them, one of them gave 1 over n to the 5th, one of them gave 1 over n cubed, one of them gave 1 over n 4th, but they don't vary very much in the probability. So 15% becomes 10% or 20%, but that's it.
But that's for uniform priors. If you take logarithmic probability distribution for the slope, what's going to happen?
Well, I can't think of any reason why you would pick logarithmic for the slope, but obviously you get a very different, I'm not sure logarithmic in what sense. Logarithmically favoring flat.
Yeah.
Well, if you have logarithmic statistics.
Yes.
Not a logarithmic potential, but logarithmic statistics favoring flat. I'm not sure whether it's logarithm or exponential, but one or the other of them will tend to very favor a lot of e-foldings.
Yes. So what's the reason for taking one over another? Because it's just a prior.
At this point, it's simply a somewhat arbitrary example to illustrate that there's no compelling reason to believe that there were a very large number of e-foldings. So at this point, somebody needs to, better than me, needs to do a landscape analysis of these kind of things and try to make a more serious argument. At this point, I take 3 parameters, which seem to me not to be specially chosen in any special way, and just throw a dart at the parameter space. But you're perfectly right. I mean, one should, and you are right. This was a harder question.
Thanks.
Any last question?
Yeah, inflation itself doesn't determine the curvature of the universe. It determines omega k, not k, the amount by which curvature gravitates. And what inflation does, it says, doesn't matter what k is, after inflation, it will contribute very little to cosmic expansion. Therefore, omega k is near to 0. But since inflation is an incomplete theory, something has to have happened before that fixes the global topology of the universe, period. Now,
To fix the
global topology of the universe.
global topology, yes.
Yes,
Double
something had to
nuclear.
have happened before inflation. Therefore, for a theory of that to be viable, it's not sufficient to say I will tell you that k is negative or that omega k is close to 0. You need to give a number. You need to say, in this particular version, it's 10 to minus 3. In another theory, it's 10 to minus 4. In another theory, omega k is 10 to minus 5.
Were you sleeping during my talk?
Yes. Yeah.
Thank you. Next question.
I'm sorry. You're saying it's
I'm not sure
necessarily
what the
10.
question is. I tried to explain.
You're saying it's necessarily 10 to minus 3?
The curvature?
Yes.
Of course not.
Oh, well, that's what
I
I'm
said
asking.
over and over again, I don't know. We could detect it at a level of 10 to the minus 3. We could detect it, and it would be meaningful at a level of 10 to the minus 3. 10 to the minus 5, it wouldn't be meaningful, but we're not going to detect it. But if we could detect it at a level of 10 to the minus 5, it wouldn't be meaningful in the sense. At 10 to the minus 2, where it's already been detected to be 0 at that level. So 10 to the minus 3 is the place to look.
Okay, I think we have to stop. I think we have to stop now, and you can continue this over coffee. So let's thank Lenny again.